Happy New Year, everyone, and welcome to the first GCSE Livestream of 2023.
Yes, welcome everyone, and a big welcome to you, Pete. I'm very excited that you'll be joining me as host this term.
Thanks, Laura. I'm excited to be here.
And I see you're not joining us from a reservoir today.
Definitely not. No, it's about minus 50 million in Yorkshire today. I think I'll save my live location filming for the spring.
Very sensible. Maybe we can plan a computer science summer road trip and visit some computing landmarks.
Sounds great. I've always wanted to go to Bletchley Park, home of the World War II codebreakers.
Oh, it is fantastic, Pete. And speaking of cracking codes, today we're going to be joined by Diane Dowling from the Raspberry Pi Foundation, who is going to help us crack algorithms.
See what you did there, Laura. Anyway, so today Diane will be taking us through our first session on standard searching algorithms. She's going to cover those that we use in GCSE computer science, and the first one we're going to look at is linear search.
Sounds great. Shall we welcome Diane to the stream?
Hi, Laura and Pete. Lovely to meet you.
Hi, Diane. Welcome to the GCSE live stream. It's great to have you.
Thank you.
So, Diane, you'll be taking us through the linear search today.
That's right. Yes, this is the first of two I'm doing. So I'm doing linear search, and then I'm going to follow up with binary search in a few weeks' time.
Sounds great. And remember, everyone, if you have any questions for Diane as she's presenting, you can send them in the chat or by using the question form below.
Pete really enjoyed his first opportunity to do the point. Diane, if you're ready to go, you can take it away.
Yeah, sure. Okay, thanks very much. Okay, so just check we got the slides. Excellent. Okay, so I'm going to talk to you, as Laura said, about linear search. And the reason we start our exploration of standard algorithms with searching is because it's a really common task. Very often your computer programs are going to be looking for some data within some huge collection of data. So every time you go onto like an online shopping store and maybe you're looking for a pair of trainers, the program behind the scenes is going to be finding the amount in stock or the price of the trainers. You might be looking for a piece of music on a playlist. You might be searching the catalogue of your local library to see if it has a copy of a book that you need to read. And in all these cases, a searching algorithm is going to be used to find that information. So let's home in on the problem of a library. And let's imagine that without a catalogue that you're going to be looking for a book. So we can see here a typical bookshelf for somebody who's got lots of books like I do. And let's say that Laura is going to visit my house and she wants to see if I've got a copy of Harry Potter and the Chamber of Secrets. So Laura, how would you find that book on my shelf?
So because I'm a kind of super organized person, I'd expect them to be arranged alphabetically, and I would look for books that have authors with the same surname that starts, or the same letter surname that starts, that you're looking for, and then I would look in that particular area.
Okay, so Laura's much more organised than I am. And unfortunately, Laura, you're going to be really disappointed when you visit my home because I don't file my books alphabetically, not even nicely colour-coded, as is quite trendy these days. So Pete, you don't look like you're quite that organised. So how would you go about looking for the book if we know that they're not sorted, if they're not in any kind of order?
Well, you see, now I noticed that they weren't alphabetically organised. So I would probably, because I've read that book before, I'd probably just look for the shape or the colour of that book and see if I could recognise it.
Okay, so, you know, I mean, I'm sure that kind of algorithm will work in the future with more machine learning and image recognition and things like that. But obviously, when we're searching for data, we don't normally actually, the computer can't look into the data. It has to handle the data in a much more systematic way. So when we start to learn about searching algorithms, we tend to really simplify the problem. So what we start by doing is just looking for an item in a very simple list which is typically stored as an array or a list in Python. And you'll normally be presented with a list of numbers, like a list of integers, like the one we can see here, or a list of maybe names, something very simple that we can work through this process of searching. And in an array, each element in the array is indexed. So the first item in the array, we can see here, is at index 0, because computers love to count from 0. And the last item, in this instance, we've got 8 elements in the array, and the last item is 7, index 7. So we can see here it's got this value 5. So we talk about the index and the value. So just to reiterate, the first item is index 0. Here it has value 12. And the last item here has index 7. And inside that element is the value 5. Okay, so looking at a linear search algorithm then, which is the first algorithm we're going to look at, or the only one we're going to look at today, the purpose is to find an item in a list of items. And as we saw earlier with our example of the books, the items can be in any order. And you can see here that the numbers are just in kind of some fairly random order, probably the order in which they've been added to the array. And the linear search works by starting right at the beginning of the list. So it starts out in index position 0, and it looks there to see if it can find the item it's looking for, and it carries on one by one right through the array. If it finds the item, it returns the index number of the place where it found it. And if it doesn't find the item, it returns -1. And you may ask, why -1? It's just called what we call a rogue value. It means that this isn't a possible index position. So we know that the item hasn't been found. And we'll see that in the pseudocode when we look at that in more detail. Okay, so let's just go over the basics again. So let's imagine that we're looking for an item that is in the list. So here we're looking for the value 16. So this is the item we're searching for. And the algorithm is going to start at the beginning. It's going to look at 12, that's not 16, 23, that's not 16, 2, not 16. And then it finds the value we're looking for. And at the end of the algorithm, this value, the index position where the item was found, is going to be returned. So the algorithm will return the value 3. And if we look at the situation where the item is not in the list, so this time we're looking for 13. So again, we look at 12, 23, 2. We keep on going right through to the end of the list. We don't find the value 13. So the algorithm will return the value -1, indicating that the item has not been found. So let's have a look at the pseudocode. So hopefully you can see this on the screen. The function is called linear search. We can see that 2 parameters have been defined. The first one, items, is our list, so our list of items. And the second one, the search item, is the item we're looking for. And we start by initializing a variable, and this is going to be the return value. So we've called this found index. So it's the index where the item was found. And we initialize it to -1. And this is because we're going to assume, in fact, that we don't find the item in the list. So this is the default position for the algorithm. And then we set up a loop, and we're going to iterate through the list. So we're going to use a variable here, current, which is going to be the current index, the slot that we're looking in. And we're going to start at 0, and we're going to go right through till the end of the list. And on each iteration, we're going to compare the value at the current position of the list with the item we're looking for. And if it matches, we're going to set found index to be that current value. So this is where it picks up the index value where it's found the item. Remember that if it doesn't find it, it's just going to stay at -1. So when we finish, when we've been through all the list, we'll have one of 2 situations. We've either found it, in which case we've got a real index position, or we haven't found it, in which case we're going to return the -1 value. And that value is returned by the function. Okay, so when we've written an algorithm and we've tested it and we make sure that it works under all circumstances, then the next question we always want to ask ourselves is how efficient the algorithm is. And when we're thinking about searching algorithms, we can determine their efficiency by measuring the number of comparisons that have been made. So how many times have I had to look into the collection of data to see if it's the item that I'm looking for? And this is the kind of key question that we want to ask. So let's sort of go back to the algorithm and also the pseudocode and see how many comparisons that we make. And in fact, interestingly, we compare every item on the list. So we start at the beginning and we iterate right through to the end of the list. Okay, so let's think about how many comparisons that actually is. I think I'm going to ask Pete this time. Pete, what is the maximum number of comparisons that we need to make when we're looking at this list?
Okay, so you just said that we have to look at every item in the list. So we have to check the total number of items in this list, which would be 8, right?
That's absolutely right. Yeah, because we've got 8 items in the list. The maximum number that we need to make will be 8. And Laura, under what circumstances do we actually need to make all 8 comparisons?
That would be if the item we're looking for is the very last item in the list, or if the item is not in the list at all.
Yeah, absolutely. Okay, so just going to confirm that on the slide. So the maximum number of comparisons is the number of items on the list, which in this instance is 8. Obviously, if our list was much bigger, if we had 1 million items, we might need to make 1 million comparisons. And we would actually need to make that number of comparisons. As Laura said, you know, if it's at the end of the list or we don't find the list, we have to go all the way through the list. We have no option. But we don't always need to make the maximum number of comparisons, but the algorithm is always making the maximum number of comparisons. So here, for example, with the example that we looked at earlier, the item is actually found halfway through the list. So we don't need to make the maximum number. We could just stop when we find the item. And this is what we need to do to make the algorithm more efficient. So to make it more efficient, we just need to stop basically when we found the search item. And when we want to stop at a conditional place, we need to use a while loop rather than a for loop, because a while loop is a condition controlled loop. So what it's going to do is it's going to iterate all the time that a condition is true. So in this instance, we're going to keep on going all the time the item is not found, which means that we could stop halfway through or quarter of the way through, or we could go on to the end, okay, until we found the item. So let's look at some modifications to the pseudocode. So you can see here that the loop has been changed from a for loop to a while loop. And because we need a condition here, we want to keep on looping while we haven't found the item. Then we're going to set up this variable, an extra variable here, found, and we're going to set it to false. Again, we're going to assume that we haven't found it. So notice we assume we haven't found it and that the index that's going to be returned is -1. Again, we're using that same default condition. But this time, when we find the search item, as well as storing the index position where we found the item, we're going to set this variable here, found, to true. And we call this kind of variable flag. It's kind of like, it's a Boolean flag, basically. It's up or down, it's on or off, it's true or false. So we start off with it being false, and when we find the item, it's true. And on the next iteration of the loop, the looping will stop. And again, we're going to do the same thing at the end. We're going to return the found index. Okay, so these are my modifications, and I really would like to ask at this point whether this algorithm will always work. You know, if I tested it, will it always give me the results that I want? Is there any circumstance under which this algorithm will fail? Pete?
Well, so Laura earlier said that we sometimes have to go right the way to the end of the list, and we're talking about also the algorithm continuing to go while it's not being found. So what happens if we haven't found the item and the algorithm keeps trying to check even after it's gone to the last item? So then we'd have the current variable will be incremented, and we'd be looking at we'll be trying to compare against an item in the array that was out of range of the array, so beyond the scope of the array.
Yeah, perfect answer. Because the mistake we found, and this is a type of logic error which you may have encountered already in your programming lessons, I'm sure you have, but this is the kind of error where your code won't crash. Well, actually, your code will crash, actually. So I'll explain in a moment. As Pete's already said, it will actually crash. But, we've assumed that the item will be found, and this loop will finish if the item is found. But of course, if the item isn't found, the loop won't finish until actually the program crashes. And as Pete says, the circumstance where that happens is where the index will go out of range. And this is a really common problem with any kind of algorithm that uses an array or list in Python, is where you're iterating through the list, but you go beyond the end of the list, or sometimes you try to go beyond the start of the list. You're going the other way. And if the index value is not a valid index value, then you will always get an index error, an out of range error, because you've just done something stupid as far as the program is concerned, something really common as far as programmers are concerned. And, even experienced programmers will encounter this, which is why it's so important always to test your programs. Okay, so it's this line here that's the problem, the one that's highlighted in red, because it's saying here that if the list of items indexed by current is equal to the search item, but as soon as current goes higher than our maximum index, then this program is going to crash. So we've got to stop that happening. So we have to make a further adaptation to stop that happening. And what we're going to do is we're just going to change the condition that controls the loop. So you can see here the modification that we need. It's only a little one, really. It's only on a single line. But we need to say not just loop while found is false, but only keep looping while the value of the current index is less than the length of the list. And in this instance, then we won't go beyond the end of the list and the looping will terminate. So as soon as we've got through to the last item, this loop will terminate, even if the item has not been found. And obviously it will return -1 under that situation. Oops. Okay, so what you've seen then here is you've seen the kind of first version of the linear search algorithm, the one with the for loop that iterates right the way through the list. And you've looked at a more efficient version of the algorithm, which uses the while loop, which stops searching once the item has found. And you can see, we've looked at pseudocode in this session, but you can see some real code examples on the platform. You can see examples in Python and C#. And you can also, underneath the code examples, you'll see there's a GitHub link. And if you click on that, you can get downloadable versions with some test data that you can play around with. And it's really good to experiment with the code. You can experiment with, removing the other conditions for a loop and forcing the error, and just see, how the algorithm works until you feel fully confident with it. Okay, so do we have any questions?
Brilliant. Thank you so much for that, Diane. I really enjoyed your example of the bookshelf, as it gave us a real example that we could keep coming back through as you went through the algorithm. And also the coded examples you showed were also really helpful. And it's great that, our viewers will be able to go and interact with those afterwards as well. So thank you.
Absolutely. Yeah, that's right. And I could really visualize using the algorithm to find a book. I can see we've already had some great questions from our audience. Are you ready to move on to some Q&A?
Yep, definitely.
Great stuff. Okay, so I'm just looking at one we've got here. It's quite a complicated one. This one says when you were showing us the index out of range issue, the algorithm only checked the value at a position in the array while that position was less than the number of items in the array. And then the question is, why did it not use equal to for this? In other words, I think what this person's saying is, won't it miss checking the last item in the array?
Okay, that is a great question. I'm just going to try and put the slides back up again if I can. Okay, can we just share the slide deck again? Yeah, perfect. Okay, let me just go back a little bit because I think it was. Oh no, it was here, wasn't it? It was on that last point, wasn't it? This one here, why it was less than.
Yeah.
Yeah. Okay. Yeah, it's a good point. So, like, why do? Yeah, when we miss the last item in the array, so yeah, we're keeping going while current is less than the length of the list of items. This goes back to the issue of the last index position being one less than the length of the list. So let me just go back and find a slide with the list on. Yeah, this one here. Okay, so this is really the key point, and this is an area where you really have to test, as I said previously, any algorithm that uses an array really carefully, because if you go out of the range, if you go beyond the end of the list, you'll always know because the program will crash, like we said earlier. But the biggest danger is that you actually stop short of the end of the list and you miss looking at the last item. So when you're testing your searching algorithms, you always want to test with the thing that you're looking for being right at the beginning of the list and right at the end of the list. And you may remember from your computer science lessons that this is boundary data. This is data which is right at the extreme of the section of data that you're looking for. And this is really important. So let's just reiterate. The length of our list is 8. Okay, but the value of the index of the last item is 7. Okay, so what we mustn't do is we must not look at position 8, or sorry, index 8. We look at the 8th element of the array, but not the item with index 8. So again, if I go back to the array now, sorry, go back to the program, that one there, current has got to be less than the length of items. The length of the list of items is 8, but current must always be less than that, because if it's equal to it, if it goes to 8, then we'll crash because we're going beyond the end of the list. And that's where the difference comes. Does that answer the question, do you think, Pete?
I think it's answered perfectly. Thanks, Di. Yeah.
Cool.
So if we had a really large data set with thousands of items in it, this would be really inefficient, Diane.
It would, yes. I mean, it would be okay. Like, we always talk when we look at efficiency of like best case and worst case. The best case is the thing we're looking for is right at the beginning, in which case this algorithm is going to be amazingly efficient. If the thing we're looking for, like think of the bookshelf, the first book we pick out, brilliant. But at the worst case, we have to go right to the end of the list. So as you said, Laura, if we've got 1 million items, we're going to do 1 million comparisons. And you think we're trying to find a book on Amazon, for example. Imagine how many books Amazon have in their bookshelf.
I've got. Have you got time for one more question, Dan? Is that all right?
I think we do, yeah.
You mentioned earlier on that you might also search the other way. What did you mean by that? If you're searching sort of back to front?
Well, obviously, when you're coding, Pete, you can write your code to go anyway. It would be quite unconventional. I'm not aware of any searching algorithm that starts at the back and goes to the beginning, although clearly, there might be a circumstance where you might want to do it. But certainly when we're processing arrays generally, we don't always just go forward. And in fact, when we're looking at sorting algorithms, there's an algorithm called the insertion sort, which actually does backtrack through an array. And so what you'd have to be careful is when you're moving backwards, that you don't try to go backwards beyond the first slot. If you code in Python, you will find you get a kind of curious effect in like a sort of wrapping effect. But that is that's a particular Python thing. You won't get that in all programming languages. So yeah, just be careful that you stop at 0 and that one end, and that you never go past the length of the array -1 at the other end. And that's
right.
a sort of golden rule, basically.
Great, thank you.
we've had another question from the audience, Diane, which it kind of links to my point about the efficiency, and that was, is it possible to make linear searches more efficient by maybe chunking it into maybe sublists?
Okay, well, okay, so a linear search, the way I've explained is the way a linear search works. So, you know, a linear search algorithm, the whole point of it is a linear search. It goes slot by slot by slot. And when we have data that is totally unordered, we don't know what the order of the data is, that's often the only approach we can take, is to systematically take each slot. What we're going to learn in the next session is that if our data is ordered, then there are far more efficient ways of searching for it. And in fact, the person who asked the question, you know, has kind of moved towards the approach that's taken in that kind of algorithm. So yes, there are definitely, you know, far more efficient ways of searching for data, which we will learn in the next session.
Great stuff. All right. Thank you for your questions, everybody. And thank you so much for joining us, Diane.
It's been a pleasure.
Yeah, it's been a great session. And I'm pleased to say you're back with us for our next session on the 8th of February.
That's right, yeah. And we're going to look at a binary search.
Fantastic. Can't wait for that. And if you haven't already, you can book your place for that session using the link, here we go again, below. Okay, thanks very much for joining us, Diane, and we'll see you on the 8th.
Okay, bye.
Thanks, Diane. Okay, so we've put together some questions for you to test yourself on everything you've learned today. You will find them by typing the short link below into your browser, and you can have a go at those.
Missed my chance there again, or didn't I? Anyway, don't worry if you find any of the questions tricky. There's loads of helpful hints to guide you to the correct answer. And all of our materials, don't forget, are mapped to the exam board specifications for AQA, OCR, Edexcel, Educast, and WJEC to make them directly relevant for your GCSE studies.
Please do let us know how you found today's session by filling out the feedback form below. Are you ready, Pete? And let us know if you have any suggestions for topics that you would like us to cover in the future.
Okay, well, thanks very much for joining us, everyone, and we will see you next time.
Thanks, bye.
Bye.